Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC1004 Physical Chemistry. This is lecture 8. And as usual, please scan your attendance using your new ID number, right? Okay, in lecture 7, we discuss on the Gibbs free energy. So this is just a recap, and the gist of that of the lecture 7 is that if the value of delta G is negative, the forward reaction is spontaneous. If it's 0, the system is at equilibrium, and if it's positive, the forward reaction is non-spontaneous. And delta G always corresponds when the at constant temperature and constant pressure, and this is the relationship. So today we are going to have another physical entity that we're going to introduce. Alright, before that, what's the criteria for spontaneity in a process? So there are 3 factors that can influence spontaneity of a change. As you have seen before, is the enthalpy change, the entropy change, and the temperature. So this next entity that we're going to discuss on is the Helmholtz free energy, or symbolized as delta A. So let's consider. So we've talked about a condition when the condition is at constant pressure. So there's also a condition in which it is at constant volume, so we're going to discuss on that. Okay, so if you have a constant volume, so that means there's no expansion work involved. So based on the first law of thermodynamics, so you have this dq is equals to du. So the closest inequality can be written as, so you have here, this is a relationship you have seen before. So this ds minus dq over dt can be substituted to being ds minus du over dt. Alright, and so if you actually multiply that by t, so you get t ds minus du equals to 0. So if you actually rearrange the equation, so you have du minus t ds equals to 0. Alright, so this equation looks something like the Gibbs free energy, except that it's a h here. So this gives rise to a new thermodynamic quantity known as the Helmholtz energy A. So A is equals to U minus Ts, as you have seen before, versus G is equals to H minus Ts. So if you take the derivative of that, so you have du minus Tds minus S dt, and because we look at conditions at constant temperature, so this will actually go away. So hence you're left with only this part of the equation. So this says that, okay, for a system at constant volume and temperature, the reaction is going to be spontaneous if the value is less than 0, and equilibrium if it's equals to 0, and not spontaneous in the forward direction if it's positive. So to summarize, so delta A is negative, the forward reaction is spontaneous, it's 0, the system is equilibrium. So it's only as in delta G, if it's positive, it's not spontaneous in the forward reaction. Okay, so it's only spontaneous in the reverse reaction. So now let's recap back, although I already mentioned. Okay, what's the difference between the Helmholtz and the Gibbs free energy? So the criteria for delta A is it's at constant temperature and volume, while delta G is at constant temperature and pressure. Now if you look at most of the chemical reactions in our everyday life, and even some in our lab experiments, it's always occurring at constant temperature and pressure. So in a way, delta G is kind of more popular than delta A. So its popularity matters. Alright, okay. So now let's look at maximum work. Alright, so we have talked about delta A and delta G being able to actually determine the direction of changes. So that means it depends on the signage of the values that you get. It will tell you the spontaneity. But delta A and delta G they also have other important applications, which is related to work. When we talk about work, we have to go back to the first law and the second law of thermodynamics. Now, remember that this is the first law of thermodynamics, where you have the energy and the heat and work. And the second law says that, this ds is equals to dq over dt, and if you rearrange that, you have this equation dq equals to tds. So because of that, okay, you can rearrange this, combine the first and the second law, so you have du equals to tds plus dw. If you rearrange this equation, that gives you dw equals to du minus tds. That looks familiar? Yes, that is dA, right? Which is the Helmholtz free energy. So what does it say? It says that as W refers to the work done by the system, and because work done is negative, right, the signage, so the most negative value of W is known as the maximum work by the system, and that's also signified by A. So A, because Arbeit is the German word for work, so A is taken there as the initial for Helmholtz. So I hope I pronounced that correctly. Alright, so hence you have dW maximum is equals to du minus tds equals to dA. So if you want to convert that into measurable change, so the maximum work is equals to delta U minus tds T delta S, and that is the delta A. So in other words, the change in Helmholtz function is equal to the maximum work accompanying a process. Okay, so A sometimes is referred to as the maximum work function or work function. So hence you have seen here, delta A doesn't only signify the spontaneity of a process, it also signifies the work done by the system. So let's look at an example how we can actually apply what we have learned. So glucose is oxidized to carbon dioxide and water at 25 degrees. So you have that. So calorimetric measurements by using a bomb calorimeter. And this experiment, you will be doing that in year 3, physical chemistry 3 experiment. Alright. So, and in that experiment, you are actually measuring at constant volume. In all the experiments you have done so far in physical chemistry is always at constant pressure, but this one is at constant volume using bomb calorimeter. So the delta U is given by this value and delta S is given by this value at this 25 degrees Celsius. So the question is, how much of this energy can be extracted as heat at constant pressure, and what is the work done? Now, so we have to pull back what we have learned before. So delta H is equals to delta U plus delta N RT, and this delta N refers to gaseous states only, and heat at constant pressure is also Q, right? So which is equals to delta H, and because delta N is going to be here, the reactants is 6 gas minus 6 of the 6 of the products minus 6 of the reactants of the gaseous states. That will give delta N equals to 0. Hence delta H, so this part of the equation becomes 0, so delta H equals to delta U, so you have delta H is just this value. So work is equals to delta A equals to delta U minus TdS. So all you have to do, you have this value for delta U, you have the value for T, which has to be converted to Kelvin. And please be very careful, right? This is in kilojoule, but this is in joules. So make sure that you convert this into joules first, and then you can actually do the equation. So do not be careless, because this is in kilojoules. So be very sharp. Your eyes have to be very sharp. Okay, so that gives you minus 2862 kilojoules per mole. Hence, what this means is that the combustion of 1 mole of glucose can be used to produce up to 2862 kilojoules of work. Okay, so as you can see here, so the value of delta U is this, the value of the work is 2862. It's more than that of the delta U. So the maximum work available is greater than the change in internal energy because of the positive entropy of reaction as a result of the conversion of the glucose molecules into smaller molecules. So it breaks up, okay, from so it becomes smaller molecules. So increasing additional particles to the system will increase the number of ways that the energy can be distributed in the system. Okay, so the reaction will produce more particles, will have a positive entropy change, so that leads to this, the higher amount of maximum work. So most of the time we talk about expansion work, the PV work. So let's talk about the non-expansion work. For example, you can have this electrical work as an example. So let's recall what we have learned before. So this is tying back everything together. All right, so H is equals to U plus PV, right? And du is equals to dq plus dw. So this is when we first talk about enthalpy, this is when we talk about the first law of thermodynamics. So let's combine these two together. So dH is equals to du plus, so we take the derivative of that gives you dq plus dw, because we combine this, and if we break this, expand this, you have pdv plus vdp. Now you also know that G is equals to H minus TdS. Take the derivative of that, so you have this. Now let's combine this and this, so you have dG equals to all this stretch of equation. This isn't complicated, trust me. You just have to sit down and rewrite back this equation without looking at the slides. Okay, try to work this out, and this is just deriving, putting things together. It's very simple. So when the change is reversible, so you will just add this little subscript here, okay, and so dq is equals to tds, and if the change is isothermal, so dt becomes 0, so this expression will be gone. Okay, so you are left with this. Okay, so once you have that, so this cancels out, so what you have is dg equals to dw plus pdv plus vdp. That's equation 5. Now there are two types of work. We have the non-expansion work, or what we call the additional, for example electrical work, and you have the expansion PV work. Now you remember that the expansion work done by a system depends on the volume change and the external pressure, so you have this W is equals to minus PdV. Alright, so this reversible work is really the expansion work plus the additional work. So if you look back at equation 5, we can actually expand this equation by saying that, okay, so this reversible work is the expansion plus additional plus PdV plus VdP. And because the expansion is minus PdV, alright, so this then cancels out. So what you have really, dg is the additional work plus VdP. Now, if we are working, if the change occurs at constant pressure, then we simplify this further, okay, by making this 0. Then what you have is dg is equals to additional work. So delta G is equivalent to what you call additional work. So equation 6 means that at constant temperature and pressure, the maximum additional or non-expansion work is given by the change in Gibbs free energy. So there you go. Delta A gives you the the maximum work, and delta G also signify the non-expansion work, the additional work. So they are not only for explaining spontaneity of a process, they also explain on work. So let's put this into practice. A patient has taken a total of 1 mole of glucose drink in over 2 days. This is like energy drink, right? How much energy is available for sustaining muscular and nervous activities from the combustion of glucose? Okay, so given that you have delta H combustion is this and delta S is this. So taking delta G is equals to delta H minus T delta S. Okay, so you have this. So it means that if you translate that into additional work, delta G additional work is equals to sorry, this should be kilojoules. Okay, I missed the J here. So the glucose taken could supply up to the maximum of 2,867 kilojoules for the patient's activities. So this is really good. When you are doing activities, you're doing exercise, mountain climbing, for example, and you want to know how much energy bars, energy drinks, how much food you should actually bring to sustain how much activities that will take up. So you can actually calculate, and even for patients, doctors can actually calculate how much needs to be given, how much food needs to be given, and how much that will actually supply in terms of sustaining the patients. So thermodynamics is not only for chemists, for engineers, it's also for biologists, for medical application, for your extreme activities. So it's really applicable in daily lives. So that makes thermodynamics really cool, right? Okay, so now let's talk about the relationship between delta A and delta G. You can somewhat see that, based on the equations and so on, there's a relationship, between delta A and delta G, and that's what we're going to do in this part of the lecture. So you have a general reaction as such. So delta G is given by this expression. Okay, you have H equals to U plus PV, and if you assume that this is an ideal gas, so you can expand this to delta nRT, right? And if you put this and this together, so you have delta G equals to delta U plus delta nRT minus TdS, right? You rearrange that and you have this. Okay, and this looks familiar, delta U minus T delta S, that is actually delta A, right? So there should be a delta G here. Okay, so delta G is equals to delta A plus delta nRT. There you go. So the relationship between delta G and delta A is that it's equals to delta A, delta G is equals to delta A plus delta nRT. And delta N, as if you have seen before, it's actually the gaseous product minus that of the gaseous reactants, the number of moles. So let's apply that. So calculate the standard Helmholtz energy of formation of methanol at 298 Kelvin from this Gibbs free energy, and assuming that the hydrogen and oxygen are perfect gas. Okay, so delta N, so this is 0 minus that of 2.5, so you have minus 2.5. So you can derive it if you can't remember this equation, but if you can just simply take equation 7 and just plug that. You have delta A given. Sorry, delta A is what you want to find. You have delta G given. You have minus that of minus 2.5. That gives delta A equals to minus 160 kilojoules per mole. Alright, so really this is so this lecture 8 is actually the last part of this lecture series. So what I hope that you're going to do is, as you realize that in this lecture we take back all the equations from the first law, second law, and also, you know, like we are tying, we didn't talk, it's not so much about the third law, but tying that with these two free energies. So this is the last part of the lecture series. So in the next lecture, what we are going to do is to actually recap everything that we have done from lecture 1 to lecture 8 and put everything together. Your job is to actually read this lecture, go over it, and at the same time look at all the lectures and look at all the important equations. You don't have to memorize all the equations. This is not a memory test, but look at the relationship so that you know how to derive one from another. Okay, so today we learn about Gibbs free energy, Helmholtz energy, and how they are related to one another, to each other, and how they are also related to work. Okay, so until next week, okay, take care, stay safe. Whether you think you can or think you can't, you're right. So always think positive. Alright, take care, stay safe. Assalamualaikum warahmatullahi wabarakatuh. Bye for now.